Hi everyone, in this video our team will present you the exploration of artistic style transfer. My name is Huan Ting. I'm here with my teammate Zachary to walk you through our defined machine learning tests, experiments, and the results. Let's take a look at our machine learning task. As mentioned in the title of our project, we focus on neural style transfer. In contrast to the typical formulation of a supervised learning problem, where the machine learning task is to take some input and learn a generalizable mapping to the desired output, the goal of neural style transfer is to use deep neural networks to combine the visual style of one input image with the content of another to create an output image. Since the goal of style transfer is to combine the style from one image with the content from another, we need to use a loss function different from the type usually found in the regression or the classification problems. Three types of loss are typically defined for style transfer tests: content loss, style loss, and total variation loss. Content loss is a measure of how well the output image captures the content of the content image. It is the mean square error between the features of the content and the output image. Somewhat similarly, style loss is a measure of how well the output image mimics the visual style of the style image. It is computed by the mean square error between the features of the gram matrix output of the style image and the output image. We will not explain further about the gram matrix in our video, but feel free to look it up. The total variation loss, on the other hand, is a measure of how noisy the output image is. It is defined as the total sum of absolute value of y plus I plus 1j minus yij plus yij plus 1 minus yij. Finally, the total loss is computed as content weight times the sum of content losses plus style weight times the sum of style losses plus the total variation weight times the total variation loss. In our style transfer, we chose a base model and designated one or more layers as style layers and content layers. Then using the base model as a base, we construct the style transfer model by inserting content loss and style loss modules after the appropriate layers. Each content loss module remembers as its target the features at that layer inside the baseline model, corresponding to the content image. Similarly, each style loss module remembers the features corresponding to the style image at that layer. We explored and tuned our neural style transfer model based on 4 parameters: the selection and combination of style and content layers, style and content weight, optimizer and learning rate, and total variation weight. We conducted the tuning using 2 pre-trained models as the base: VGG19 and AlexNet. We evaluate the performance of the models and various hyperparameters by comparing the content loss, style loss, and the qualitative visual inspection of the output images. For our dataset, we chose to use the dataset of best artworks of all time, collection of paintings of the 50 most influential artists of all time. This dataset contains a CSV file of artist information, 2 zip files of collections of images. Here we use the image from the resize.zip file, and we resize the image to 720 and square crop it to 720 times 720. We also use some real-world images from other sources, which is also resized to and cropped to 720 times 720. Here are the images used in our experiments. We use Professor D and Yan's photo adapted from Edmonton Journal as content image, and use one of Vincent van Gogh's self-portrait in our dataset as style image.
Now we will give an overview of the experiments we conducted. We did experiments using both models, the one based on VGG and the one based on AlexNet, but this section will focus on the latter. And these are the 4 hyperparameter categories that we conduct experiments on, as outlined earlier. The first experiment is to select style layers. And AlexNet has 5 convolutional layers. And the selection of style layers is important because each layer in AlexNet is responsible for identifying different types of features, and which types of features we use to define style loss will affect the nature of the style reproduction. So now we try different combinations. On the right is the output images generated by using the first convolutional layer, the second, the third, the fourth, and the fifth, respectively. As you can see, this confirms that each style layer, each convolutional layer is responsible for different types of features. The first one is mostly responsible for the color, the second captures the coarse brushstrokes, etc. And this reflects the nature of AlexNet and typical convolutional neural networks in general. The first layer is able to pick up on smaller features. In this case, it's the color, which requires very little knowledge of the surrounding area, the surrounding data in the image, whereas the second layer is able to look at the features that have passed through layer 1 and have been gone through the max pooling layer, and is able to combine smaller features into bigger features, in this case the brushstrokes. And the latter three layers don't seem to contribute much on their own. So on the right here is the image made using the first two layers as the style layer, and the second image is when we use all 5 layers as style layers. As you can see, they're very similar, but the latter seems to have better reproduction of finer details, the color blending, and so on. But the first one is quite good as well. So we suggest that using the first 2 layers, because it's less computationally intensive than using all 5 layers, would be preferable in some scenarios, for example, when we're operating with limited memory or limited computation power, whereas using all 5 layers is preferable in general, because it captures more of the style. Next, we look at content layers, which is important for a similar reason as the style layers. But as we can see, the selection of content layers and the number of style layers has very little effect on the output image. They all look about the same. And this is probably due to the fact that when we initialize the input image to feed into the style transfer network, we in fact we initialize it using the content image. So it becomes less important which content layer we use. It is able to see a slight difference in the way that in the strength of the style application, and this could be because by varying the number and the selection of content layers, we are also varying the absolute value of the content loss, which changes the relative weight of the style loss and the content loss within the optimizer. But in this case, we can see that using content layer 4 is adequate, so we select this as our content layer. Next, we compare different optimizers and different learning rates. So typically when we do artistic style transfer, it's common to use LBFGS because it tends to reach a better optimum. But it is also more computationally expensive. So here we compare it with the more familiar stochastic-based optimizers, Adam and Adagrad, and we test them each with different learning rates. And the results show that LBFGS is indeed slower compared to the other two. It takes 10 seconds to train the model for 300 steps, whereas with Adam and Adagrad it takes only 3 seconds. Here we compare the outputs generated by each. The first column is LBFGS, and the second and third are Adam and Adagrad with different learning rates, 1, 0.316, and 0.1. So clearly, the images generated by an LBFGS optimizer are the most convincing in terms of style transfer, and for both Adam and Adagrad, LR equals 1 is too high. The optimizer skips past or misses all of the minima, resulting in this noise. And this makes sense because, in fact, the typical learning rate for Adam and Adagrad are much lower than 1. At LR equals 0.1, which is the middle image of the third row, Atom is able to do some kind of style transfer with some color reproduction and some trace of the brushstrokes, but it's not as good as LBFGS. And in the case of Adigrad, it totally fails. There's no color of the style image, and there's also no trace of the brushstrokes. And this is probably due to the design of Adigrad. It keeps a sum of all of the gradients in order to slow down more quickly when the gradient is steep. But this leads to it often stopping too early before even reaching the minimum. Atom does better because it uses momentum as well as an exponentially decaying average of the past squared gradients, which allows it to adjust its learning rate, or rather adjust the weight changes more appropriately. And unsurprisingly, when the LR is very low, none of the models using any of the optimizers are able to do much style transfer at all. Using the optimal learning rates for each optimizer, we look at the loss curves, and the behavior at very low learning rates is common across all three. The style loss is decreasing, but the content loss is increasing. And the reason for this is when the learning rate is so small, none of the optimizers are able to find a minimum that minimizes both the style and the content loss. And because the absolute values of the style loss is so much greater than those of the content loss is sacrificed in favor of style loss. And here we see that a similar conclusion where Adigrad converges to relatively high loss and it converges slowly, whereas LBFGS achieves a lower loss and it does this rather quickly. Next, we look at style weight by varying the style weight from different values. As you can see, when the style weight is low, the optimizer, the model, has very little incentive to minimize the style loss. So the output is rather similar to the original input. Whereas when the style weight is very high, the loss function is dominated by the style loss, and very little regard is paid to preserving the content. And so we find that the best balance is when style weight is around 100,000 in the middle. And similarly for content weight, the trend is in the opposite direction. When content weight is 1, relatively more of the loss is dedicated to the style loss, whereas when the content weight is quite high, the optimizer has no incentive to reduce style loss. So we choose content weight equals 1 as the optimal content weight. Finally, we experiment with the effect of total variation loss. Up to now, we have not included it in the loss function. In other words, we have set the total variation weight to be 0. Here we try different values of TV weight. As you can see, visually, the outputs are almost identical. TV weight, although it's supposed to decrease noise, it doesn't seem to have any effect. And comparing the loss curves, they are almost identical in every case. So we conclude that there's very little value added when we include the total variation loss. So having explored AlexNet and explored the VGG-based model, we choose the best hyperparameters for each one, and we determined that the VGG-based model is better at doing style transfer, and we produce some new style transfer images using that model, and they are presented here. And that's the end of the presentation.